The schedule, I went ahead and added in some readings that I had not provided. So for both last lecture and for the next 4 lectures. All right, so that is there now. The assignment is available for assignment 3. Let me just show you a quick description of it. So it's again in the form of a Colab notebook, and you're going to be submitting as a Colab notebook. So it's housing prices, but it's housing prices in Ames, Iowa within the last 20 years. So houses are not $20,000. They're like a couple $100,000, let's say. So still cheap for California. You're training a neural network, and you're trying to create a low mean absolute error. So you're trying to basically predict housing prices where the absolute error is not too much, right? So if you're predicting $230 and the actual house price is $215, then you have an absolute error of $15,000. And that's what you're trying to reduce, the validation error on that. Although there are more training samples than there are in the Boston housing data set, there's still so few that you probably want to use some form of k-fold validation. Okay? So the mean absolute error that you're going to be looking at is on that validation set. One thing you'll want to do, I mentioned on Monday that the notebook, the Cholette notebook, had an error in that it leaked information from the validation into the training data set. Mo, do you remember what the information was? Frank? Oh, sorry.
So when we seriously standardize our like housing prices to, because it's a much larger scale, it's in like square footage. We did it before cross-validation, so we were doing it because we used the information of all the other data, so it wasn't really different.
Yeah, so basically when we calculated the mean and the standard deviation, it was not just the mean and the standard deviation of the data we were training on, it included the mean and the standard deviation of the validation data, so that's now getting incorporated into the training data in our normalization, and so that's not good. So instead of normalizing one time, we surely should be normalizing every one of the k-fold cross-validations. So when we extract our validation and the remainders are training, that's what we should create the mean and standard deviation on. All right. So I did the first, so the bad news is the grading of the exams is not done. Worst bad news is the assignment 2 is not done either. The good news is half of the exam is done. And so I expect the rest to be tomorrow. And I'll get the assignment done after that. So certainly by this weekend. The first thing, what's the first question do you guys think that I graded? You would think so, but that's not very interesting to me. Comments about the class, yes. So that's where I went first. And it's easy to grade too, because everyone provided 3 things, or at least said I can't think of a third thing. And so therefore, got full credit. But I liked reading that. One of the things someone pointed out, and it's true, is that assignment 2 was just messing with hyperparameters, right? If you don't like messing with hyperparameters, you do not like deep learning, okay? Because if you consider the depth of the network and the size of each layer and the choice of the activation functions and so on as part of hyperparameters, which in a real sense it is, then all you're doing in deep learning is messing with hyperparameters. Okay? So your next assignment is also messing with hyperparameters. But we have somewhat more things to mess with. So you get to completely decide what the structure of the neural net's going to be. Again, the optimizer, the activation functions, hyperparameters. You can try and do this without looking at the data, but I do not recommend that, right? Actually, one of the first things you always want to do when you are doing training is look at your data and become very familiar with it. So there are references, you can see the actual data, and then you can also go look at a description of the data, which is very useful to see what does this field mean, what does this field mean, and so on. All right. One thing you might consider doing, every training instance has a unique value in it. Why might that be good or bad? Josh?
It might be bad because our neural network might overfit to those IDs.
Yeah, that's something really easy to memorize on, right? I don't have to look at all the rest of this data. I could just memorize that ID and then know, oh, that ID goes to that output and that ID goes to that output. So that's probably why you will want to remove that. Categorical information. So here we have not only numeric information, but we actually have categorical information like what's the type of the roof. That might or may not be one of them, but composition, an actual string, composition, or tile, or something else. And so we've got these categories that we need to deal with. We can't just feed those strings directly into our neural network. We have to either remove them, does not use them for the training, or convert them to numbers somehow. Leo, how might we convert? Let's say we had, instead of, let's say it's roof type, and there's 5 different roof types as strings. How might we convert that to a number?
You can map them to 1, 2, 3, 4, 5.
Okay, map them to 1, 2, 3, 4, 5. That's will certainly work. The numbers 1, 2, 3, 4, 5 there are somewhat different from the numbers 1, 2, 3, 4, 5 if we're talking about number of bathrooms, right? Don't they? I mean, because first off, 2 is more than 1, right? When we have 2 bathrooms, it's more than 1 bathroom, and 3 is even more than that. So we have this ordering relationship between them. But we don't have any ordering relationship between our 5 different kinds of roof types, do we? So.
Break them into different categories, or like different parameters that are all 1 or 0.
So different one-hot parameters makes sense, yeah. So basically have category shingles, category tile, category slate, and those others. And then basically one of them will be a 1 and the rest will be a 0. So that's a perfectly reasonable way to go. And that's what this article tells you about. And part of what this article tells you about is how to actually do it in, could be NumPy, but we're not actually going to be using NumPy. We will be using NumPy in order to deal with this matrix of information, these tabular information, I guess is what I would call it, right? It's basically like an Excel, well, it is a spreadsheet that we are reading in. Does anyone use Pandas? Okay, so Pandas is what we're going to be using, which basically is the Python way of dealing with tabular data. How I'll be grading it, whether you fix the leaking validation, okay, that's just kind of a binary. Did you fix it? Well, I guess you could fix it wrong, but did you fix it or not? The effort and creativity you've shown in trying to create a model. Okay, so you're going to create a log that just shows things you've tried. All right? And then also what your actual absolute error that you got is. Okay? But it's not like you don't reach a certain error and you fail the assignment. It's just do the best you can. And how clear your notebook is. So don't just put a swath of code in there. Throw in some text cells, right? This lets us do that with some descriptions of what's going on. Don't copy the existing housing regression text descriptions. Make your own. They don't have to be as long and fancy, but provide some sort of a description like you're trying to walk someone through, because that's what notebooks are for. All right? And I'm expecting between 10 and 20 hours, so don't spend more than 20 hours, but don't spend 1 hour. Don't spend 5 hours either. So about that range, all right? We're using Pandas. We read over the network from the CSV file that's out there. And the first thing we do is, because the author recommends this, recommends throwing out a few outliers in the data. So Ames, Iowa does not have a bunch of really large houses, and the few that are there really are much separate from the rest. So we're going to just remove the rows whose square footage is greater than 4,000. So in this case, the square footage is actually broken down into the first floor square footage and the second floor square footage. So we add them together. So this is an example of some Pandas usage. There's a reference to a Pandas cheat sheet and also to the Pandas website in the notebook. And here's an example of what we got. So order is just an ID number. PID is like the property ID I think the tax assessor uses. And then we got a bunch of stuff, much of which I don't know because I haven't read it. But the frontage, right? How many feet you have along the street. The area, presumably in square feet. The street, is it paved, or I guess there are other alternatives. The alley comes in as not a number because of a weird thing that Pandas does. So it's actually in the spreadsheet, it's in A. The condition, what year it was built, so that's numeric. The overall condition, which is numeric. The overall quality, which is numeric. A bunch of categorical information. And then at the very end is the year sold, which is relevant, right? Because there might be a general increase in prices from year to year. And then sale price, and guess what? That is your target. One thing that's really important to do when you're doing your regression is make sure this is not in your training data, right? It should be your Y. Make sure it's not part of your X, or you'll make it very, very easy for your neural network. So there's about 3,000 total samples and 82 columns of data. And I went ahead and added some code to prepare training and test data sets. So we just create a mask, basically, and of ones and zeros, and pull out particular rows of the data frame, depending whether the mask is on or off. So we have 85% training data, 15% test data. And we extract the data and labels. Basically, we pull out the sales price as the label. We drop the sales price. And we also drop, in this case, all of the categorical columns. So columns have a data type. We drop the non-numeric ones. All right? So you'll need to, at some point before this, convert those categorical ones to some sort of numeric. But to begin with, just forget about the categorical ones. Get something going. And so that's how we extract these. So we can see we have about 2,400, 2,500 training data. And the shape, instead of having 82 columns, we're down to 38 because we lost all our categorical ones. Some hints. We've used standard optimizers like Atom or RMS prop, but we don't know how to change the hyperparameters for them. So, right, because we are accustomed to just specifying the optimizer in a string. So that says use the Atom optimizer with all the defaults. If you want to create an optimizer with specific values for your hyperparameters, you instantiate it like this, and you provide your parameters, and then you just provide it as the optimizer here. So the optimizer parameter can be either a string or an actual object. One important thing, and that is that test data set. What do you think I want you to do with that test data set? Santi.
Oh, wait, the test one?
The test one.
Until the end.
So at the end, like right before you submit, what are you going to do?
Try it out.
Yeah, you're going to try it out and see what the mean absolute error is. Okay? But really, just wait till then. Okay?
Did you set a specific seed for this so that we're going to all have the same test data that we're going to be working on?
You should all have the same test data that you're working on, yeah, as long as you don't add anything up above those cells that create the training and test data. Okay? All right, so only evaluate it once. Actually, you can evaluate it as many times as you want. It's more a Schrodinger's cat type thing, where it's not until you look at it that it's ruined. Okay? As long as no one ever looks at it, it doesn't matter. Okay? But once you look at it, you're not allowed to rerun stuff. Okay? That is this assignment. Any questions? All right. And my guess is you're just not getting to worry about it until you get back from break, and that's fine. If you have questions, you should email me. Is that right? No. If you have questions, do not email me. Instead, Piazza. In a private post? No. In a public post so everyone can see the wisdom of your question and the silliness of my answer, or vice versa. Okay. But it'll be information that everyone will want to know. Plus, maybe I won't be around and someone else will answer the question.
Sorry, what's the due date?
Let's talk about that due date and make sure we're all agreed. So it says here, October 28th. Let's just go ahead and check. Not that it's possible that there'd be an error, but it happens to match the date in the schedule, and that happens to also be a Monday. So those all three are good things. The stars are aligned. Okay. Now on to convolutions. Convolutions are what we need to learn about in order to deal with convolutional neural networks, abbreviated as CNNs. So we're going to be talking about CNNs over the next few lectures. Today we want to look at the building block of convolutional neural networks, which is convolutions. So convolutions are used in image processing, forget neural networks for a moment, as a way to apply effects to images. So for instance, I don't know whether you can see it, but this on the right is more blurry than this. And that's done with this convolution operation here. We can also have a slightly different kind of a blur. We can do line detection. So the right-hand side shows us this basically capturing, in this case, it looks like it's capturing horizontal lines and maybe diagonal, but not the vertical lines. Okay, so we can choose with the appropriate choice of a convolution kernel what kind of edges we're getting. Horizontal, diagonal one way, diagonal the other way, vertical, or really any combination of those. Here's an example of a combination of those where it's capturing all of the edges. So horizontal, vertical, and diagonal. That is all I really want to show you right now. Just leave this right here. So in the past with machine learning, right, prior to neural networks, you would never feed the raw pixels of an image into a machine learning algorithm. Instead, you would do some pre-processing on that image and extract features that would be useful to your machine learning algorithm, like edges. What a convolutional neural network does is allows a neural network to learn convolutions such that it can extract features like this, like edges, and other sorts of things. Okay, so it'll learn what it finds is useful to extract from images in these low-level features. So what is the convolution operation? Let's look at that. Let's say we have two 3x3 matrices. So the A matrix and the B matrix. And we want to convolve these. It's really just a pointwise multiplication, and we add them together. Okay? So multiply each associated pair and sum them. So it gives us a single number. Does that make sense? All right. So let us create a 3x3 matrix. And this is going to be our convolution kernel. And let's say we have an image, which is going to be larger. So we have a giant 5x5 image. And this image is very simple. We're just using black and white. Okay, so 0 is white, black is 1. And our image is going to look like good image. Let's look at this. Is that the image I was using? All right. And we want to do some edge detection on this, in particular horizontal edge detection. So let's look at how we do this in this example. So we pick a special kernel that is designed for horizontal edge detection. So this is a horizontal edge detection kernel. And let's look at what happens when we apply this kernel to the entire image. First, let's talk about what that even means. Basically, what we're going to be doing is taking this 3x3 matrix and putting it on here and calculating that convolution. And then we'll move it over one, and we'll calculate again. And we'll move over one and calculate again. And we'll go down one and over and over and over and down one and over and over. If we do that, such that this top left edge aligns with this top left edge to begin with, and at the ending, the bottom right aligns with the bottom right, we're going to be turning, so after this operation, we're going to have a 3x3 matrix, and let's look why. We're going to take this to here. Okay, so let me, we're starting here. What are these, by the way? They're not ones. Yeah, those are zeros. I'm not going to write them in. It makes the picture look better that way. Okay, but we'll just remember that those are zeros. So we're going to apply this to this. So let's look what happens. That's going to be 0 times -1 plus 0 times -1 plus 0 times -1. So the first row gives us zeros. The second row gives us zeros because of this row here. And the third row is going to give us 1 plus 1 plus 0. So our final result is a 2. That goes here. So this is centered at 2, 2. We took this kernel and centered it at 2, 2. If we center the next kernel, or we center the kernel now at 2, 3, we'll be over here. Is that clear where we are so far? Any questions? All right, so let's look what that's going to be. The first row is going to give us all zeros, right? The second row is going to give us all zeros from here, this multiplication. And the third row is going to give us, Susan, what are we going to get from the third row as our sum of products? So we got 3 here, right? But it's going to be, now we're working on this purple one. 1, right, because 1 times 1 plus 1 times 0 times 1 times 0. So we get a 1 here. And we move it over one more to the right. And Brendan, what do we get?
0.
Yeah, all 0 because this entire zeros. So we're going to get zeros. That's easy. And then we move down 1 and back to the left. And we're going to get, in the first row, 1, -1, right? Because this 1 times this -1, 0, and 3 ones. So 3 positive ones and a -1 gives us again a 2. Right? So this one comes from being centered at, Morgan, where's this one centered at?
That one's centered at the one that's in the bottom of the square.
1, 1, 2, 1, 3, 1, 3, 2. Yep. And then we can do this one, which is going to be, I'm going to quickly say 3. And the next one's going to be 3. And we do the bottom one, -2, 0, 3, so that's a 1. And -1 plus 3 is a 2. And 0 plus 3 is a 3. Does anyone argue with any of these numbers? They could be wrong. 2, 3, 3, 1, 2, 3. 2, yeah, it matches at least what I got this morning. All right. Here's a weird thing that happened. We did this convolution, and we started with a 5 by 5, and what did we end up with? 3 by 3. And that picture over there, did it get smaller? I mean, if it was 1 pixel smaller on each side, you couldn't tell, but it didn't. It's the same size. What could we do to make this the same size as that one on the right?
You could add zeros.
Okay, we could add zeros all around the edges, let's say. But why? Where? How did it get smaller? It's because we started centered at 2, 2. If we'd started centered at 1, 1 and we entered centered at 5, 5, we would have ended up with a 5 by 5. So let's try that. Let's try see if I can redo this. What would it mean to be centered at 1, 1? That means it'd go off the edge, right? The kernel would look like this. Well, I know how to do calculations with these, but what do I do here? Zeros. That's the most common thing that's done. So we could, this is called padding. And the most common is 0 padding. But sometimes what's done is you just copy the edge over. And sometimes what's done is like you copy from the other side, like you had some wraparound asteroids game or something. But most common is 0 padding. So let's just use 0 padding. And let's go ahead now and augment this. Okay, so fill in the centered at 1, 1, for example. So we're going to add in here the missing ones. Zero, 0, 1. Same thing, 0, 0, 1. 0, 0, 0. Wait. Now we have to be up here. Right, we're up here actually, right? So it's the whole thing is going to be 0 up top, right? Because sorry, let me get this right. So we're going to be moving over, over, over. We're centered. Right now we're centered here. We're going to become centered here, 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 and here. So this is a 1. This is a 1 because we still get that 1. This one's going to be zeros because we have 3 zeros here. Zeros, zeros. And then we need to move down. And so it's going to be 0, 0, 2. Yes? And if we're down here, someone do that for me. Loudly. -1, 0, and 2, which is a total of 1. And here, is this where we are? Yes, we're here. So -2, +2, is 0. -2 and 0, and 0 is -2. -3, -3, -3, -2. Oops. And finally, let's see, we were here, now we're going to be, we were here, that's 1, 5, right? Now we're centered at 2, 5, that is 0 and 2 and 2 and -2. So it's 0, 2, 2, -2. Okay. All right, so now we've got something that at least is the same size as our original.
Second to the top. 0. So it's 0, 0, and then 2.
So this one is here, and that's a 2. I agree with you. All right. Let's just kind of look at this. It's no longer a bitmap anymore, right? Because it's not zeros and ones. But it's numbers coming out that we can try and interpret. And let's shade in the 3s. Let's shade in the 2s too. What does this look like? It is kind of, it's a little wide here, right? It's 2 pixels wide, but it is sort of the edge between 1s and 0s. The top edge in particular. Because there's a bottom edge right here, right? And we're not capturing the bottom edge. In fact, the bottom edge would be negative numbers, the way this goes. So what this captures is a boundary where we've got 0s and 1s, and we don't care what's in the middle. Okay? Which kind of reflects this. This is a boundary between 0. So right here is a boundary between 0 and 1. And this one's also a boundary between 0 and 1 where we don't care about this 1. Same here, this is a boundary and this is a boundary. These are all boundaries, and these are all boundaries because we don't care about the middle. So here we have a boundary between these two, and then there's a boundary between these two. But if we've got a bunch of 1s together, a whole solid swath of 1s, what are we going to get as our value? 0, because we'll have -3 from up here and +3 from up here. So that's what it's doing, is detecting edges. Thank goodness we do not have to design these convolution kernels. Who's going to design them? The what? No, researchers don't. Well, in the past they've designed them, but these days with convolutional neural networks, the network is going to come up with these weights. Okay, it's going to learn it. But here's the nice thing about it. We share this convolution across the entire image, right? We say we're going to use this one horizontal image detector across the entire, because this is useful no matter where we are. Because with images, we have this translation invariance, right? This idea that if we moved stuff in the picture, like if we just sort of moved everything up and put, I don't know, different background in the back, that it's the same stuff. From what we've learned so far with fully connected layers, it would have to learn independently that if there's to recognize, let's say, a square up in the top left versus a square in the bottom right. But if it can learn a convolutional kernel to detect squares, it can use that same one throughout the entire image. Okay? So there's less for it to learn, and this applies anywhere throughout the image. Okay, so this is a case where we are taking advantage of our knowledge of the problem domain, that is images, and the fact that we have patterns that'll be anywhere within the image. Okay. So we've got ourselves now one horizontal edge detector.
Why do we choose the kernel of size 3x3?
Why 3 by 3? So we can make bigger ones. Why would we want 5 by 5 and not 4 by 4? Do you have any thoughts? And I'll give you a hint. It's the word that used to be written here, centered at such and such a location, right? So if we want it to be centered, then, and we want it to do the same on both sides, then it has to be odd. So we can use a 3 by 3, we could use a 5 by 5. What does a 1 by 1 convolution do? It scales. It's multiplying by a scalar, right? So not that interesting. 3 by 3 convolution kernels are very, very common. 5 by 5, 7 by 7s exist. They're less common. In a couple weeks, when we talk about different architectures for CNNs, we'll see some different uses of those. You had a question, Jack?
Is there anything to do about maybe, like, for example, we have a sense of like maybe how wide some of these like edges or system boundaries could be? Would having a bigger kernel help us detect like sort of maybe wider lines?
They could. We're going to actually, yeah, we would not have the ability with a 3 by 3 kernel to determine that we've got a 5 pixel wide line, right? That's not possible. But we're going to be chaining these together in layers. And so that's a good segue into that idea of going into layers. Again, I'm not going to be saying we have a neural network here. I'm going to be sort of designing this by hand. But, yeah.
Like, how do you go from like grayscale to like 1?
Oh, let's do grayscale right now. Okay, before we go on to another level, let's say that these values are 0.2, this is 1.0, this is 0.9, this is 0.3, and so on. We're going to do the same exact thing, and we're just getting numbers that are floating point instead of non-floating point. So when you have a grayscale image, conceptually, it's easiest probably to look at that as just a floating point number between 0 and 1 for each of the pixels. Although practically, it's normally an integer between 0 and 255. Yeah. So, but you can always go back and forth on that scaling. Does that answer the question?
Yeah.
Okay. The most common kind of padding is this zero padding, what's called, so there are two issues. We have pad with what? And in this case, 0 is the most common. And then the second question we have is how much padding? If you do no padding, what happens to the size of the original image? It shrinks by how much? Let's call this W, the width of this.
I think you like subtract 1 from the kernel width and then divide that by 2.
Yeah, we can, so basically, let's say n by n goes to n minus, I'm going to just say W over 2, the floor, which is the same thing as W minus 1 divided by 2, right? Does that one make sense? Right, in our case, since our width is 3, we're reducing it by 1 on, sorry, that's not quite, is that right? That's not right.
Uh,
We need two of those.
by 2, yeah.
We need two of those, so. If we have 5, we're going to be smaller by 4. I think it's just going to be, which is maybe exactly what you said, minus w plus 1. So minus 2 in this case, and minus 2. Because basically what we're losing is this side and this side, which is the total length divided by 2. So that's how much padding. One possibility, no padding. The second possibility, half padding is what it's called. And that's what we just did. So n by n goes to n by n. Well, if that's the name of this one, what do you think the other name is for the other possibility? Full padding, I like it. And what happens to our image? N by n goes to, well, actually, what does it do in full padding? Full padding basically says, take the kernel as far as you can while it still covers at least one element. So it'd be way up here. Okay? So we'd be basically adding 2 here and 2 down there. So instead of, yeah.
In what situation would we rather use like half padding over just full padding?
So you normally want to use 0 half padding.
Right.
That's the standard. Okay? It's kind of a pain if the thing sort of slowly shrinks. And so this is the common case that you want to be using, is 0 half padding. I'm just providing this for completeness. And I'll leave that number as an exercise, but it's a little bit of arithmetic, I guess. All right. We don't need this anymore. Let's say we have created some kernels. All right? We've got ourselves, we can't quite get to the second level kernels yet. We need to learn about depth. So I'm going to talk about depth now. Let us say we have an image that is not black and white, is not grayscale, but instead is color. Okay, and we'll make it 5 by 5, and it has a depth. How many dimensions to the depth, Raji? So we've got a color image. What are the components of a pixel in color? 3. 3 they are. Red, green, blue. Yeah, so we'd have, this is by 3, and this is red, and this is green, and that is blue. If we tried to use a 3 by 3 kernel with this, we would run this 3 by 3 kernel on the red dimension, a plane, and then on the green dimension, and then on the blue dimension. But unfortunately, maybe our kernel wants to take into account something about the relationship between the things in those 3 channels. Right? Maybe it's, for instance, a kernel that's trying to detect gray. How do we know what a gray pixel is here? Say again?
Is there a combination of 3?
What about that combination of 3 makes it gray? The sum combination is, Daniel?
They're equal?
They're equal. If red equals green equals blue, that's gray. So that'd be something we could do, but we would need to have access to simultaneously all of the pixels in this depth here. So this is our kernel. This is our image. which is color. And we have 3 by 3 by 3. This 3 here matches this 3 here. This 3 by 3 is something we get to decide. We get to decide how big this kernel is, but we know the depth has to match the depth of the input. So now, what's our output of this going to be? What's the size of this going to be, assuming we have half padding, if we apply this kernel? Rory. So you're going to say 5 by 5 by 3. You would think so, but let's look at this a second. You might think so. Actually, you do think so. It's a reasonable thing to think. So if we apply this cube, and we're going to first put it in the top left corner here, it's going to do not 9 multiplications. It's going to do 27 multiplications, right? It's going to multiply this front face by the red channel, and the green face by the green channel, and the blue face by the blue face by the blue channel, and then sum them all up to live exactly one number.
Are you also going to sum between like different colors of the result?
Well, that's what this is going to give. So this is going to give us 27 multiplications centered at 1, 1 in our original image. So it's going to be with some padding that I'm not showing at the top and the left. It's going to be these values plus these values plus these, that is, all of these values together, all multiplied by their appropriate kernel components, and then all summed together into a single number. So for instance, we could say, for this area here, is it gray or not gray? Possibly. We'd have to come up with an appropriate kernel for that, but I think we could come up with gray. Does it make sense? So we're just operating on more data. Instead of operating on 9 values, we're operating on 27 values. And we still end up with one number. And so we're going to end up with 5 by 5, but it's going to be handy to show it by 1. This is one convolution. We don't want to do just one kernel applied to our image, though. Right? We might want to get lots of different pieces of information, low-level information about our image. Where are there horizontal lines? Where are there vertical lines? Where are there diagonal lines? Where are there splotches of orange? Where are there other sorts of things? Okay? And the way to do that is more kernels. So we can have, let's say, a horizontal kernel. We could have a vertical kernel. We could have a diagonal kernel, let's say that way. We could have a diagonal kernel that way, all 4 of these kernels. And so we're going to come up with, and I'm going to not make them to scale, but this one is going to yield a 5 by 5 by 1. This one's going to yield a 5 by 5, they're getting smaller and smaller, by 1. And this one's going to yield a 5 by 5 by 1. So now we have in here captured information about horizontalness in these various areas. Captured information about verticalness, about diagonal in one way, about diagonal in another way. Okay? And they're all the same size, even though you can't quite tell it from this picture. But they all say 5 by 5, so they are the same size. 5 by 5 by 1. Mo.
But they're not all in the same one, right? Like, if it's 5 by 5 by 1, then we only have 1 of these, right?
We have 4 of these. 1 5 by 5 by 1, 1 5 by 5 by 1, 1 5 by 5 by 1, and another 5 by 5 by 1. So we've got 4 of them.
Each one of the 4 stores
Each of the
Each of the 5 times 5 times 1.
Each of the 5 by 5 by 1 was generated by a separate 3 by 3 by 3 kernel. So we had one kernel for horizontal, one 3 by 3 by 3 kernel for vertical, one for diagonal one way, one for diagonal the other way. Okay.
Do we have to make all the what do we have? What's the result? What's that called? The result after we apply the kernels, that's convolution.
The result of this is just the output of this layer.
Okay.
So, but we're gonna organize this in a slightly interesting way in just a moment, rather than having 4 separate things just hanging around.
They all have to be the same size. The results?
In practice, yes. Your convolutions would all have the same padding and the same size. We'll see some slight differences from that in a couple of weeks, but in general, yes. And for a reason, because basically what I'm going to do is I'm going to slap these together. And to slap them together, they better be the same size.
Would it ever be useful to just your kernel to be 3 by 3 by 1, and then your output would be like a 5 by 5 by 3, so you're doing the kernel for each layer?
You could theoretically do that, but you normally want to be capturing from your original input a combination of the features at each layer, at each depth here. And this is going to be even more apparent as we go to the second layer. So this is our first layer where we came out with these 4. Okay, well, we created these, my hand, let's say. Santi, you had another question?
Yeah, so in this case, we're kind of compressing, it seems like we're compressing the color a little bit, like that's what we're doing.
Yeah, we're
Yeah.
yeah, we are compressing the color. The color is now, in fact, lost in some ways, except for whatever this convolution managed to capture.
But we could equally compress in other directions as well.
Spatially, we're restricted very much, right? Spatially, we are restricted to this 3 by 3 by 3 cube here and only using information from there. So we know that this output so this particular value there has a receptive field in the input. And that's basically what pixels does it see from the input? It's from 1, 1 to 2, 2, right? It's basically 4 pixels. 1, 1, 1, 2, 2, 1, 2, 2. The top left 4 in 3 dimensions in the red, green, and blue planes. Okay. Every pixel here, every value here, we can point to and say which pixels did it come from. And as we go farther down the line, in higher depth, we'll still want to be able to do that. Hey, I've got this tensor here, right? This matrix. If I look at this value here, what were the original inputs it came from? And it's going to be some square value in there. All right, so here's what we do. We take, let's use some color. Let's make this one be red, and this one be purple, and this one can stay white. So we're going to take these, and we're going to put them together. So we have a 5 by 5, and we're going to have the first slab of this, the first layer in this dimension. Is the problem with layers is we have 2 uses for the term layer, right? We have the layers of the neural network, and we have now our layers in our 3-dimensional matrix. But in any case, this is the horizontal guy, right? This one, horizontal. This one's vertical. This one's this way. This one's this way. Next, we're going to put the vertical one behind it. It fits, right? Because the vertical one's 5 by 5. So this one is the vert. After that, we're going to put the next diagonal one. So this is the upward diagonal one. And finally, we put the diagonal that way. Okay. So we processed the original image. We applied some convolutions to it. And now we have this new data, this output from that layer that is 5 by 5 by 4. We know where the 5 by 5 came from, right? The 5 by 5 came from the input plus knowing what the padding was that we were using for these convolutions and the convolution size. Whenever we have half padding, we don't care about the convolution size. But if we use no padding, the convolution size matters because that tells us how much it's going to shrink. That's where the 5 by 5 came from. The 4 comes from 1, 2, 3, 4. It's the number of convolutions, let's call them of kernels, in the previous layer. All right? You with me? Now I want to create a stop sign detector. Okay? I'm going to detect hexagons at layer 2. I'm going to create a kernel. I'm going to do a 3 by 3 again. So this is a stop sign kernel. Let's just call it Octagon. Octagon kernel. We know it's 3 by 3 because we decided it's 3 by 3, but the question is, how deep is it? Willow, any thoughts? So this was layer 1. This is the output of layer 1. Although we should probably throw in a nonlinearity, which is a ReLU, but that'd just be a ReLU on every single value in here. So this is the output of layer 1, which is the input into layer 2, right? Why did we make this guy 3 by 3 by 3? Where did this 3 come from? Okay. How many layers are here? So that has to be 4. Exactly. So your depth of your convolution kernels, you don't get to decide. It's decided by the depth of whatever's incoming to you, and you just match it. You get to decide the height and the width, but it's normally 3 by 3. What you really get to decide is how many convolutions, how many kernels do you want in each layer? We decided to have 4. That's where we got our 4 here, and that determines the size of the next convolution. Well,
And what's the use of the 3 times 3 times 4? Like, does it just puts them all into one layer, or?
here's what it's going to allow us to do, and let's look at it right now. We want an octagon. So we're going to have an octagon detector here, and I am going to use colors again for this, okay? So I want an octagon detector. So let's just look at an octagon. Composed of what sub-elements? Horizontal, vertical, diagonal left, diagonal right, which is so handy because that's what we have. So how do we determine, hey, there's an octagon centered at whatever this convolution kernel is looking at? Do we care about what's in the middle? I don't think we care about what's in the middle here or any of the way past, right? The middle, we don't care about the, because here's the middle. Is right there. So what do we want? We want, this is the horizontal detector, right? So we want something like a 1 at the top and the bottom. We like horizontals there. And let's just say we don't care about what happens to the rest of it. Okay? If everything else were 0, this would be a detector of a horizontal line and then another horizontal line below it. But we don't want just that. We want to also detect verticals.
These would be horizontal lines like 1 pixel apart.
These ones would be 1 pixel apart. We're going to see, either later today or when we get back next Wednesday, how we can expand so we're not just dealing with original pixels. Okay? So that if we have a 200 by 200 image, we're not just schlepping around this 200 by 200 image all this time with this little 3 by 3 looking at these tiny little micro features. So we're going to find a way that we can kind of zoom out on this stuff. But for now, we're looking on these micro features. So it's going to be a tiny little octagon. Maybe it'll be more octagon-ish. There's some horizontalness up here and some horizontalness over here. Now we got to do verticalness. So where do we want verticalness? In the left and in the right, in layer 2, because that's the one that does vertical. So we're going to have, I'm going to just pull these apart and look at them because I can't write in this 3 dimensions. So I'm going to go over here. And we're going to say, this is our 5 by 5 by 4. This one is going to be, what did I say, 1, 1, 0, something like that. And then the next one is red, right? So this one is horizontal, this one is vertical, and so this one is going to be 1, 1. And then we've got next the upwards diagonal. Help me out here, someone. So it's these guys, right? So at the top left and the bottom right, there'll be 1s. And then finally, we've got the other one, and that must be the opposite corners. So if we apply this convolution to this guy, and we have half padding, the layer 2 output is of what dimensions? If this is our only kernel. Remember, this is one kernel that's been spread to show the 4 layers of that one kernel. So what's the depth? It's 1 because we have one kernel coming out, right? One kernel in the previous layer. So that's 1. And the size is 5 by 5. And then this would tend to have larger numbers where there are octagons, or these octagon-ish things. So the key takeaways here, we decide how many kernels there are at each layer. We get to decide how big they are. In order to be stacked, they should all be the same size. Their outputs get stacked together into another 3-dimensional tensor. Tensor is just like an n-dimensional matrix. Okay? And the depth of that determines the depth of the convolutions in the next layer. All right?
Do you have to do it in terms of like, oh, I know that this layer does this specific thing, or do you just like make a bunch of layers and like it'll figure out how to do it?
It is the latter. You make a bunch of layers and let it figure it out. We are going to look in several weeks at how we can visualize what is actually sort of being learned by each kernel, which is kind of interesting. You got a question?
Can I just over here? So the output of this, if there's a high number, it means there's an octagon that's centered in that location?
A high number would mean there's an octagon that's centered at that location. But it's center-ish, right? Because our concept of a horizontal line is a little fuzzy, right, because where the black and where the white is. But this provides a concept of it. I'm not claiming this is actually a very good octagon detector.
How do you decide how many kernels like going to?
How do you decide how many hyperparameters to have? So between about 2011 and 2015, there was a lot of work into coming up with convolutional neural nets, where really the question is, how do you decide like how many layers and what activation functions to use and so on. And within each layer, how many kernels and what are the sizes of the kernels. And then I'll add this new feature in just a moment. And what spurred a lot of advance was a challenge called the ImageNet challenge. So it was, I think it's 100, no, I think it's 1 million labeled images into, is it 10,000 different classes, I believe? And the accuracy on that over that 4 or 5 year period went from like around 75% to in the very high 99s, 98s. And almost all of that was architecture. Some of it was learning to train better optimizers. But so much of it is just designing that, what it's going to look like correctly. Yeah, Jack.
Wondering why it's still 5 by 5 by 4?
It's not 5 by 5 by 4. It's 5 by 5 by 1. Yeah, this is our current, right? This is our kernel from layer 2. Expanded. Yeah, so it's exactly identical to this. Yeah. Question?
Yeah, so in the first layer, if our input is, since our input is only like one, I guess I wish I might have to think about it for a second.
All right. Come back to me as necessary.
I think I'm confused with this one. So our input is one 5 by 5 by 3 image, right?
Yep.
And then is our kernel just one 3 by 3 by 3 thing, or are there 4 3 by 3?
There's 4 of them. There's one here, and there's another one, and there's another one, and there's another one. And so those will all generate these 4 outputs. But yeah, this is one, and then there's another 3 by 3 by 3. And another one. And another one. And the output, exactly, is 5 by 5 by 1. Okay. So actually, let's just look. How many coefficients do we have in this? It's not a hard problem. How many in this? And in this? So 27 times 4, let's just write that down, plus here, yeah, 3 by 3 by 4, which is 36. So we've got ourselves 108, 142, which is not a lot, right? So we're really using what's called weight sharing. These coefficients are these weights are being shared in doing these operations everywhere throughout. Okay, and that provides a modicum of regularization. Really what it provides is a less powerful model, which means we're less likely to overfit. Okay.
How does
Santi?
this only apply to image data? Like, can we extrapolate these kinds of things to other?
You can. So there are a couple reasons. It's ideally suited for image data because we've got this translation invariance. We can move stuff around and we still expect the same thing to happen. Convolutional networks, by the way, do not have rotational invariance. So if you rotate something 90 degrees, it's like all bets are off. Which is kind of interesting because we don't exactly have rotational invariance either, right? If you turn your head 90 degrees, like you can't recognize faces as easily. And so there is some form of up and downness that our minds have. Well, I have to show you the pooling layer, so let me just quickly show you that, unless there are any last questions about this. So what we are trying to get out from today is what a convolution is and how they combine together from layers to layers. So you can have multiple convolution kernels in a layer, and how the outputs get stacked in another input to the next layer.
And then just a quick, make sure that I have this down too. That, in that particular, where you said in the kind of example we did, we started off with 5 by 5 by 3. We used 4 3 by 3 by 3 kernels to get the 4 3 by 3 by 1 layers, and then use those layers to determine whether or not the octagon was centered-ish at the end.
Yes, although the way you really want to think of it is we have a 5 by 5 by 3. We have 4 3 by 3 by 3s, 4 kernels, and then this produces a 5 by 5 by 4. Okay? So we just pulled it apart into separate ones just so we understood what's going on. But from now on, just imagine the output's always pasted together, slapped together. Okay? And it just so happens in the first dimension, that's RGB values. But we're doing the same operation from layer to layer to layer to layer of multiple dimensions, and just being able to look at the depth of all of this. So we're looking at all of this at once. There's a slight approximation I made, which is there's a bias too. So for each kernel, there's a bias. We're not going to talk about those much anymore, but they're there. They'll be learned.
The bias is applied after the kernel is already like do you get the 5 by 5 by 1 and then you add the bias, or you do it
How it's implemented doesn't matter. We can think of it as we do the summation of this 3 by 3 by 3, you know, the 27 things and then add 1 value, and the 27 and add 1. Or it might be that it's really implemented as you do all the 27 and then you add 1 everywhere. And actually, it's probably worth knowing also the way this convolution operator is done, especially on a GPU, it doesn't actually go 1 by 1 by 1 by 1 by 1 through here. It arranges things such that it can do, I believe it's a big matrix multiply. All right. So we will review this, because you likely will have forgotten by a week from today. And then we'll go into pooling, which is a way to shrink the image size but somehow keep some information. And then we'll go from there. So I would expect to have the exams and the assignments back to you this weekend. And when I post the exam results, I'll also post a solution on the schedule. All right? Have a good fall break.